Okay, so we're going to use Excel today to calculate a one-sample t-test of means for the problem stated here. So our biologist raised some seedlings of sunflowers, and the typical height of a seedling is 15.7 centimeters. But this biologist applied an extract from a particular plant to try to lower the height of the sunflower seeds. He had 33 samples, and he measured their heights after being treated with the extract. And we have the heights here in our spreadsheet. All 33 samples. Okay, and so what we want to do is we want to conduct a one-sample t-test. Now, the phrasing of this problem is a little unusual because they don't say the mean height was 15.7, but the standard height. But what they mean here is the mean. N equals 33 is probably good enough if you wanted to use the z-test for a sufficiently large sample size, although bigger is better. But since we're using we're going to use the standard deviation of the sample, because the population standard deviation is not provided. Instead, we're going to use a t-test since we're making an estimate from an estimate, and so this will be a little bit better for us. All right, so let's just write down H0. The mean, mu, is 15.7. and 15.7, and HA, mu, is going to be less than, since we want to know if the extract lowers the average height, 15.7. And again, the 15.7 is what the height is before it was treated, and so we want to assume that the extract has no effect, that it's still equal to 15.7, and we want to see if there's sufficient evidence to say that the mean has in fact gotten smaller. So then the first thing that we're going to need to do is we're actually going to need to calculate things like the mean. So in Excel, the mean is the average. So we're going to highlight our cells. And then we're also going to need to calculate the standard deviation, STDEV.S, and that's going to be, again, A1 through A33, same set of cells we had before. And so then we're going to need to calculate our test statistic, t-test statistic. And so recall our formula. It's the difference between the mean of the sample and the mean of the null hypothesis divided by the standard deviation divided by the square root of n. And we have n equals 33 samples. It says right in the problem. And remember, this is the standard deviation of sampling distribution. So this is how the mean varies, not an individual sample varies. And so we get minus 4.599. We're going to assume, I'm just going to make a note over here, assume that alpha, the significance level, is 0.05. Generally speaking, if the problem does not say otherwise, that is the default assumption. And so we want to calculate this test statistic and convert it from a t-value into a probability value to get our p-value so that we can compare it to alpha. And so the p-value, this is a less than hypothesis, so we want the probability that our t-test, our t-value, will be this value or smaller. So that is a left-tailed test, so we're going to use t dot dist. Our x value is our test statistic. The degrees of freedom is n minus 1, so in this case that's 32. and we do want it to be cumulative, so we're going to type true. Now, when you use the tdist function, it automatically does less than the value. If this was a one-tailed test with a greater than sign, we'd use tdist.rt, and if this was a not equals to, we could use tdist.2t, so that it would be two-tailed. But this is just less than, and so we just use a standard tdist distribution. And so we get this value. This p-value is less than 0.05. Remember, the e with a negative number after it is a very small number. This is equivalent to 4 decimal places, 4 zeros, and then the 3. So this is a very small number, and that is definitely less than 0.05. And so therefore, we're going to conclude that we reject the null hypothesis, and there is sufficient evidence to believe that the sunflower seedlings are shorter than 15.7 centimeters. Since there is insufficient evidence to support the null, there is sufficient evidence to believe the alternative.